James Willis is joining us from London, and he will talk about how to write parsers in functional languages.
Great. Thanks for that. Let me share my screen. Yeah, so today I'm going to be talking a bit about the work I did that I presented at ICFP this year. What I want to do here, though, is actually talk about how to use it practically, as opposed to what it is, what it's doing, and how it works. Hopefully, you can see my screen. Is that working okay?
Yes, thanks.
Okay, cool. So yeah, this is the outline for today. So the outline is I'm first going to start by briefly explaining what a parser combinator library actually is, and hopefully most of you are familiar with that already. After that, I'll be talking about exactly what Parsley is, discussing the difference between monadic parser combinator libraries and selective ones, because that's probably something you're unlikely to have heard of before. And then discuss actually what changes when we use Parsley as opposed to something like Parsec or megaparsec. And then I want to sort of touch on a few of the parsing patterns in a very shallow manner. So I'm not going to go too deeply into it, but I'm going to, for instance, sort of introduce how we can get rid of bind and replace it by applicative operations and stuff like that, because obviously Parsley is selective parser combinator library, not monadic. So I'm going to start off by explaining a bit about what parser combinators actually are. And I'm going to dive straight in with just examples. So here is a parser. It's responsible for reading any one of the characters 1 through 9, one of them, and it'll give it back to you. So essentially a non-zero digit. And I can expand on this a little bit more by adding on char 0 with this OR operation here. Hopefully you can actually see my mouse. So this is saying read a character 0, and if that fails, then try and read a non-zero digit. And so you can see we're building them out of building blocks that we already have. And most of the time we don't really just want to work with characters coming back. We actually want to do something with them. And in this case, what we have is non-zero on the front of many digits, so that's 0 or more digits, and this will form a list of characters. And then we can apply the read function of type list of character to int over it and get ourselves an integer back. So those are the sort of things you can do with parser combinators. Here's another example. We can read identifiers, which are going to be an alphabetical character followed by many alphanumeric characters. And the satisfy combinator basically allows us to read a character that matches some predicate that we give it. In this case, is it an alphabetical character? Or here, is it an alphanumeric character? So to summarize, the actual core combinators are basically satisfy, as we said, which takes a chartable function and reads a character with that. Try, which we're not really going to focus on. Look ahead and not followed by. And these are used for positive and negative look ahead respectively. Again, I'm not going to touch on those, but it's useful to know that they exist. So let's see what we can do with satisfy. Well, we can build a couple of other handy combinators. So item is the parser that reads anything at all. The predicate you give it just returns true for everything. And we can read the specific character, which we saw previously, by just saying satisfy equal to that character. And again, to show off some other stuff, EOF can be defined as not being able to see an item as the next. So there are no more characters to read. So it should be the case that we can't read a character. So just to summarize that, oh wait, no, not summarizing yet. We need some combinators. So we can't really do much with the primitives alone. So we rely on the functor applicative alternative hierarchy. Hopefully you're familiar with those, but they basically allow us to manipulate the results that come out of our parser. So F for us is parser. So we have a parser that returns A's, we can make it return B's. And pure allows us to parse things without having any computational context. So we don't read any characters when we use pure, but we do get a result back, and so on. So this is the OR operation from before. They can make choices, and using these we can build up more and more tools to make our grammars. So that's what makes parser combinators so great, is we can use regular functions to build our parsers. And what does that mean? Well, this is the normal sequence operation that you would see in the Haskell prelude. And it basically takes a list of, in our case, parsers and sequences them together one after another and returns all their results. And we can build on this by using traverse, which takes a list of values and it can transform each of those values into a parser and then sequence them together and collect up all their results. And one of my favorite consequences of this is actually how to parse strings. So if we take the child combinator that we had before, then actually reading a string is just traversing with character. So we take every character in the string and we turn that into a parser in its own right that matches just that character. And then we sequence them all together. And what that will do is make a string at the other end. And this is the sort of stuff that really attracted me to parser combinators in the first place. You can use higher order functions from Haskell to do a lot of cool stuff. So the one of that we also saw in the very first example, that's just mapping character over a list of characters. And then afterwards, basically folding them together using choice. So is it an A or is it a B or a C or so on or so on. So let's go back to our originals and just summarize with what we've seen. So one of is built out of ors and folds, and that will do any of these possible combinations. And we can use functors and applicatives to build together sort of data that we want to get out of our parsers instead of just working with strings and characters. So that's the basic idea behind parser combinators. And obviously there's quite a lot more you can say about them. Hopefully some of the stuff that I will talk about today will sort of shed a bit more light on them, but I just wanted to give a very brief overview of what they were and how roughly what they look like, basically. Are there any questions at this point? Just to make sure everyone is on the same page about what we've seen so far, at least roughly. I'll take that as a no. Great. So moving on then, what is Parsley? So Parsley is a body of work that I've been working on for the last 2 years. It's a staged selective parser combinator library. And what I'll make clear is what that means as we go through. So it's the rough sort of overview. If you look at something like Parsec, I like to characterize it like this. So Parsec's performance is okay. There are better tools out there. Parser generators and handwritten parsers obviously perform better. The error messages are also okay. They're not the best. They do look quite a lot like the grammar. I like to think, obviously not as much as a parser generator, but they're a hell of a lot more like a grammar than a handwritten parser would be. Parsec itself isn't particularly easy to debug when things go wrong. Megaparsec is a bit better in this regard. And we can't really do any grammar analysis on Parsec because there's no structure to inspect. It just does a job and results come out the other end. In contrast, Parsley has great performance. So it's a lot better. In terms of error messages, I don't have any yet. That is okay. That's on the work agenda. And I don't want error messages to impact performance in the slightest. So that's a non-issue for me. Again, Parsley looks like a grammar. It's slightly easier to debug because it's got those debugging combinators. And actually it supports lots of different analysis. And a lot of it is still future work, but the point is that they can be done. So how does this all work? Well, it works via metaprogramming. And for the uninitiated metaprogrammers out there, what metaprogramming is where your programs write programs. So when I use metaprogramming, I'm working with code as a first-class value. That's how I like to think of it. So object-oriented programming, objects are first-class values, functional programming, functions are first-class values, parser combinators, parsers are first-class values, and here metaprogramming is code as a first-class value. And so what that allows me to do is at compile time, build up the parser and analyze it and compile it and do all sorts of things to get that performance out of it. And it roughly works something like this. I'm not going to go into detail. That's what ICFP was for and other talks that I've given on this. But roughly speaking, it first gets turned into an AST with both combinators, optimization and analysis happens. It gets translated into something else, a bit more analysis happens, and then we get compilation, which generates code at the other end. And there are some practical implications of stuff that we can see along this path. So I want to sort of touch on practical things that come out of this pipeline. And the first is actually the fact that it's using an AST. So the way Parsley works is it builds an AST out of the combinators. So they're not actually doing things, they just make a tree. And it will do analysis passes and optimization passes on those. And so a problem with that is actually how do you represent recursion in those structures? And it leads to our first consequence of what it actually means to use a staged parsing library. And here is the definition of the mini combinator. So this is the one that reads 0 or more or something. And the way it's been defined now works perfectly fine in something like Parsley. In Parsec, for Parsley, this would not compile. And the reason it won't compile is because this actually generates an infinite tree. So what will happen is when we call mini p, it's going to call mini p again. But this is actually a fresh call. This is a true recursion. And so this will generate an infinite tree that we now have to traverse, and that's just not feasible. So the first practical lesson is we always have to ensure that recursive parsers have no arguments. So this Go here is physically the same as the Go that comes here. So this is a truly cyclic data structure now. So this is a finite tree, and Parsley is able to find out where those recursion points are. So that's not an issue, but we do need to make sure it's a finite structure. And we will come back to this a bit later on, because perhaps some of you are going to be thinking, well, I like having arguments to my recursive functions, and it's a bit of a shame that we've lost that now. So I will come back to that, and I'll explain how we can recover that again. So the next little nugget of information in the pipeline is actually in the optimization phases. So Parsley does some quite cool optimizations. For instance, if I write a fairly contrived parser like this, where I say fmap f onto some p, and I fmap a g onto some q, and then I combine them, what the Parsley optimizer is able to do is actually factor out that function on its own. So it makes a function that takes two arguments, an x that will come from p and a y that will come from q, and does f of x and applies it to g of y, which is what this originally was doing. And so that's quite cool. And that's using the applicative laws to do something to do this. And actually another great example is the string combinator. So we saw earlier it was defined as traverse. And if you were to unroll traverse on this thing, you'd get something like char A const onto the front of char B, const onto the front of the pure empty list. And this is quite inefficient because it's actually got to build the list as it goes through. So it's got to read the A, add it onto the front of the next thing, and so on. And so what the Parsley optimizer is able to do is actually hoist that computation out. So it will just replace it with satisfy reading an A, get rid of that, and then read a B, and then replace that result with the string AB. So it will do all of that work for us ahead of time. So really, the moral of the story is let Parsley do the optimization for you. Don't try and do it yourself. It's very good at optimizing things. And in my experience, the more naive the definition, the better it gets optimized. So that's quite a nice consequence to have around. And really, the next thing I'm going to talk about is actually where the magic happens itself. So we don't need to understand at all what this giant chunk of code is, but it's illustrating that when we wrote that natural parser before, this is actually what will get generated. So at compile time, GHC will process this parser and produce this code. So this is what will actually get pumped out. And we can see our first little hint of Template Haskell here. The way we run this parser is by using a Template Haskell splice. And I'll go into a bit more detail about what that means, again, a bit later on. And the key thing is that this happens at compile time. So all of the optimization, translations, staging, that's all a compile time operation for GHC. If you were to look at the core that came out at the other end, you would see this sort of stuff in its place, which is where all the performance comes from. So some of you might have heard of Template Haskell before. Parsley does not use Template Haskell, it uses typed Template Haskell. And there is a small difference. for those of you who don't know, it's not too much to worry about. For those of you who do know about Template Haskell, Template Haskell allows you to work with combinators where you can build Haskell ASTs at will. Type Template Haskell doesn't allow you to do that. So you're restricted to quasi-quoting. And what that means is it's a lot more principled and it's a lot safer. So there's no arbitrary building of expressions in Parsley. We have to use typed quasi-quotes, and we'll again see what that means a bit later on. But it's sort of less important to know how this works in order to use Parsley. There's some nice plugins that sit on top of it that try and help make the job a bit easier. So the next thing I want to sort of discuss is the relationship between monads and selectives before we start talking about how to use Parsley, because this is quite an important point. So hopefully we're all familiar with what monads are. They are just applicatives, but with a bind operation tacked on at the end. And what bind allows you to do is to run some operation, in our case a parser, or in our case not a parser because we don't have monads for Parsley. And what you would be able to do is extract its result and use it to make decisions about what to do next. So you'll build a new parser with that information. And that's problematic for reasons that I'll discuss shortly. But here's an example of how it might actually be used. So I can actually flip the definition on its head, the one that we had earlier, where we had item is satisfy if const true. And I can actually define satisfy in terms of item. And the way this works is we run item and get any character back. We extract that result with bind, that's called C, and then we run the predicate F on C. And if it returns true, we will just return that result wholesale. We won't do anything else to it. Otherwise, we'll fail, which is exactly what satisfy was doing originally. And as another bit more complex example, we can actually augment the identifier example from before, so that instead of just reading an alphabetical character followed by an alphanumeric one, it also ensures that it's not a keyword. So if it isn't a keyword, then we will return pure again. Otherwise, we'll return empty. So now if you try and read if with an identifier, it will fail, and so on. And so the thing to notice here is there's a bit of a pattern going on. It's my first little pattern, and it's quite important to recognize. And that's the idea of filtering. So I pronounce this operator as filter or filtered by. And what it says is you have some MX, you're going to get its result out, check it against a predicate, return a result or fail, which is exactly what those two examples were doing. And so let's solidify that by seeing it in practice. So satisfy is item filtered by a predicate, and an identifier is an alphanumeric sequence filtered by the fact it's not a keyword. So filter is quite a useful little combinator. It's a quite nice little pattern to encapsulate. The key is that something's going to go wrong. So monads seem great. They seem wonderful. They can already do some cool stuff. What's wrong with them? Well, the problem is that they inspect values at runtime. And what did I say? I said Parsley runs at compile time. So there's definitely a conflict between these two. They can't both exist. The compile bit is the key. So start by introducing what selective functors are, and then see how these two things are different and why selective functors work where monads don't. So selective functors, for those that are not familiar with them, and that's more likely because they're quite new, they consist of applicatives with either a select or a branch operation tacked on top. I choose to use branch because it's a bit more versatile and I think it's a little easier to explain how it works. And the basic idea is the first argument that comes in is a parser that returns an either A, B. And the next key thing is you have two possible parsers, one that handles A's and one that handles B's. So if an A is returned by this first value, we'll use this parser here. And if a B comes back, we'll actually use this parser here. So only one of them is going to get picked, and that choice will happen at runtime. So what's the hook? So if we look again at filter, defined by monads, we can see this nice gray box. And what the gray box is it's representing something that we can't inspect. So I can't look at Haskell functions. That's outside of my realm of control. And this X is a runtime value, so I don't know what it is at compile time either. Which means at compile time, I have no clue what happens after this point. It's essentially mx bind something, who knows, I'm just completely stuck. And so I can't generate any code from that. I don't know what's going to happen. And if we replace this definition so that it uses selectives, this time using select, which is a branch where the right side is just uses the identity function to get it out, then what we can see is that the orange structure, which is actually the parser combinators themselves, don't exist inside the gray box. So the gray box now tells you at runtime what branch you're going to take. Is it the right branch or the left branch? But you know at compile time what the two branches are. In this case, one of the branches is empty and the other one is the identity function. So that's why this works. Essentially, we know both of the outcomes that can come out of a filter at compile time, and at runtime, we get to know which one actually happens. So that's the general idea about why selectives are great and monads don't quite work. And we can see, of course, that the pattern that the monad was using here, the if then else, is capturable by selectives. So that's a good thing. So what can selectives not do? Because that's also important to recognize. And the two things they can't really do is they can't implement join, and that's quite a subtle point, and they can't persist results. So I'll come back to those later and explain what I mean by them. And actually, is there a way of getting that power back? Can we use monads without actually having monads? And the answer is yes. And I will also talk about that while I cover what things why selectives can't do these things and what those things actually mean. So now for the slightly more novel bit, the bit that most people might not know about. How do we actually use Parsley? What changes? What's the difference? So, as I said earlier, Parsley uses typed template Haskell. What does that actually mean? So here's our combinators. Here's a bunch of them. And these are all of the combinators that actually get changed. A lot of them don't because they don't have a value in their signature. So you can see we have a function here, a value here. Other combinators just work with parsers. They don't change. And so what happens when we use template Haskell is everything gets what's called WQ in front of it. And WQ is a thing from Parsley, and it is basically a value paired up with the code that represents that value. So template Haskell code is the type of, if you're using a sufficiently new version of GHC anyway, is the type of Haskell syntax. So it's a value that it's an AST that represents that value in A. And the other change that gets made is run parser now returns the code of a function from string to maybe A. So it's no longer parser to string to maybe A. Now it's code. So so it's a representation of the Haskell function we want out. That's the thing that was generated. And the way that we incorporate that back into our control flow is to use what's called a splice. So this is our first template Haskell specific operation. And what splice basically does is it will take the code that it's just generated at compile time, and it will inject it into this hole here in the code that eventually gets output. So the code you run will basically substitute what came out of there into this position, is a rough way of thinking about it. So if you have a value of type code A, splice of that value will give you back an A. And so the question really is, how on earth do we get hold of values of type WQ? And it's also worth noting at this point that we've lost applicatives. So we don't have the type classes anymore. They're gone because Pure doesn't have type WQA to parser A. So we've lost the type classes and the overloading that we used to have, but I still maintain all the same names for the operations. So we make values of WQ with the lift plugin. Now, in particular, we use my branch of the lift plugin. because it's set up nicely to work with the right things. And what the lift plugin does is it basically fills in the holes for you. So here's the example parsers that we had before, and we're going to show what changes when I adopt Parsley now. So when I use Parsley, that's all that changes. And it's quite magic. So I add a dependency on the lift plugin, and then I add code in front of values that have type WQ, and hope for the best, essentially. And we'll explore what can go wrong when that doesn't work. So now we basically say, give it the code of the read function, give it the code of isAlpha, give it the code of alpha num. So in the best case, that's all you need to do. You just add code in the right places, which is wherever you need a value of type WQ, and everything works out okay. Sometimes that isn't quite enough. This can go wrong, at least semi-frequently. And let's explore what that means. So here's my first example of something that's gone horribly, horribly wrong. So I've now tried to make the satisfy function take in the code of equals a. And this is boom. And the reason this is boom is because this isn't a function in its own right. This is not trivially liftable. And that's because it's actually a lambda. So essentially, what's the fix? The fix is we build a value of type WQ ourselves. And thankfully, it's pretty easy. It doesn't really cause us any problems. So we take the value that we wanted to give it, and that's the value. And then we do the exact same thing again, but we wrap it in quasi-quotes. So these are template Haskell quotations with an extra bar, which denotes their type template Haskell. That's the only difference. So if you're familiar with bracket bar, that's the same as bracket bar bar, except it has type code A as opposed to a TEXP, which just has no type at all. And yeah, it works fine, but no one really wants to do this. I certainly don't like doing it when I have to. Is there a better way? Yes, there are better ways. So the other thing we can do is cave, and we can make an alias for the function, call it isA. And a crucial quirk of template Haskell is we have to define it in another file. In another file is because template Haskell requires it to load itself before it can be spliced. So if it's in another file, now we can use code again. And Andres has asked a question, could code of the plugin be replaced by quasi-quoting? Yes, which is essentially what we've got here. The reason why we don't do it like that is because we might want to allow the optimizer to have access to the value too. So the optimizer might want to inspect the things we pass in so that it can do some operations on them at compile time. But strictly speaking, yeah, we could replace everything by just quasi-quotations. Another thing we can do is use the idioms plugin to chuck more junk on top of junk. So the idioms plugin allows us to write applicatively with code being an applicative thing. So here we apply the equals function to the code of A. And how that actually desugars is like this. So we have a function, it looks like app, but it's backwards, and I call it quap. And it's quap because it works with codey things, queues. And so basically, the idiom brackets will get translated into equals f mapped onto code A, or f quapped, I suppose. And so that means we'll take the code of equals and we'll quap it onto the code of A. So that's all this plugin does. It's a slight convenience. It's quite useful for other things. So let's say we wanted to compose two functions f and g. Well, we certainly can't use code. That doesn't work. So we resort to using WQ again. And we write the exact same expression twice, one with quasi-quotes and one without. And the plugin can simplify this by, we can just say, well, code of f composed with code of g inside our idiom brackets. So this is the syntax that it introduces. It's a bracket followed by a listy brace. And yeah, there's a question here, are double barred quasi-quotes different from single barred ones? Yes, they are, in the sense that this is a typed template Haskell quote as opposed to an untyped one. So this will produce a value of type code of a function, and the other one would have just produced a value of type code. And it's useful to know what the types are because the combinators are all typed. So we don't really want to be working with an untyped representation. Other than that, they are the same. It's basically just a wrapper around normal quasi-quotes with an unsafe coerce shoved in there for good measure. So yeah, we can use the idioms plugin to compose these more naturally, but there is an even better way. As I said earlier, trust Parsley to do the optimizing for you. So if we write it as two fmaps, fmap f over fmap g, then Parsley will do the sensible thing and optimize it to the thing in the middle. So if you didn't want to use the idioms plugin, just writing it in a more verbose way might well just have it optimized down to the exact same thing, which is true in this case. Okay, so are there any questions about this? I will check the chat. There is a question on its way. I can see it. Just at the moment, this will be the end of the sort of how does Template Haskell fit into this. So there's not much you need to know. And so for the remainder of my time, I will be discussing patterns. Yeah, so WQ is a general, so the question is, WQ is a general thing in the context of staging. Are you planning for this in the plugin to be separate from Parsley? So the plugins are separate from Parsley. The only reason why I forked them is because I need to avoid some of the pitfalls with the original plugin. So the idioms brackets plugin will use fmap, pure, and app. That's a problem because we have our own definitions of fmap, pure, and app. So we need to differentiate with code and quap being the units of the idioms plugin. As for the lift plugin, I think, yes, the lift plugin, it can be specified for any type class as long as it's liftable. The reason I didn't want to use lift, which was the original function name, is because it conflates with another definition. I think it's a little more immediately understandable to just see it as code. But you could just rename the function in the lift plugin so that it's just code, and it would work out. It would work out fine. So yeah, these are more general concepts than here. They're slightly specialized here for usability, but that's not a game breaker. That can be changed. Okay, so patterns. So the last bit that I want to sort of cover here is, well, we've lost monads. How do we get them back? How do we eliminate monads from programs that already have them? And so on, sort of play around with those ideas. And something that really annoyed me when I set out on my journey many years ago is that many parser combinator libraries make heavy and unnecessary use of bind. Bind is all the rage back in the day. And the problem is it made my life very difficult because I couldn't use it. And so I had to learn pretty quickly how to write parsers without bind and how to recognize when I've lost all hope and I have to resort to either hand implementing something or just not supporting it. So I'm basically going to structure this by taking two practical examples, which are themselves a type of parser combinatory pattern in a slightly different sense to the ones that I'm talking about here. But there's a sort of bigger story around here about the patterns of parser combinators, which I'm sort of trying to touch on. And the first one is the ever amazing chain R1 combinator. So briefly, what chain R1 does is it allows you, and incidentally, I think its type is a bit wrong, but that's for another talk. It allows you to take atoms of type A and separate them by operators of type A to A to A, right associatively. So you could pass, say, chain R1 of a natural and the plus operator, and have it read something like 7 plus 8 plus 9 plus 10 plus so on, and have it all bracket off to the right. That's what the R means. And here's how it's implemented with the do sugaring gone in parsec. And immediately we can see it is absolutely not helpful at all because there are 3 binds. So the aim of this is to try and get rid of those binds and put us back on a stable ground. So here's my first strategy. Here's how I'm going to start. I'm going to notice that when you have something like this, where you're doing a P and then you're following it by some function, the likelihood is, as long as the function doesn't do anything special inside, like use if or something else, a good start is to recognize this can probably be done with a parser that returns a function. So in a sense, push this argument inside the parser. So let's do that and then try and fix it so it works again. So I'm going to use reverse app. So this is where the function sits on the right and the value sits on the left. And I've changed the type, and now immediately this is all broken. So this is all wrong. So the argument needs to go. And the first thing we're going to notice is that when you have this alternative failing case, you're going to return the thing that came in. So a good candidate for replacing this x is just going to be the identity function. And then the next thing we can recognize is that we can turn this into a function of type a to a pretty easily by just removing the x. So if we flip f and have flip of fy and then just drop the lambda on either side, we now have a function. So that's that. We've now fixed it. It will compile again. That's now great. This is a function being returned. But we've still got to deal with these pesky binds here. These ones, thankfully, are easy. So it's straightforward. This is a chain of F maps and apps. So this is what applicative do notation would also be able to find for you. So basically, I'll do the translation and flip back between them a little bit. So we have a flip applied to F, which is the result of op, and we have Y, which is the result of chain R1 P op. So what we can do is fmap flip onto op and then app it onto chain R1 of P op. And thankfully, we are now sat with no binds. So this definition now works perfectly. And for completeness sake, here's what it would look like in Parsley. The differences are I've added some code. And the other thing I've done is I've removed the recursion. So here we can see that there's a recursion with arguments. I've turned that into a cyclic recursive thing, which refers back to itself. So this is all that's necessary to translate this. And I think, honestly, this is a lot nicer to read and sort of reason about than the monadic version. Yes, yeah. So essentially, why am I showing this? I'm showing here's how it should have been written. Essentially, back in the day, people used bind all over the place, and it's serving as a nice example of how to find these things and how to get rid of them. But in Parsec, at least, this is written with do notation. So that's one example, and I'll do a slightly harder one again to sort of solidify the general principles that I use when I'm trying to hunt these things down. And it's not going to be much of a surprise which one it is. It's chain L1. So same deal, except this time the associativity brackets to the left. And the same strategy is going to apply. So we're going to start by recognizing this could probably be done as a function. So I'll pull the same trick. And again, we can recognize the exact same first step. So here we're taking an X and we're returning an X. So we can do the id trick again. Now things get a bit tougher. So the key is to recognize that rest will take in the result of this left associated bit and pass it on to the next bit, so the wider context. And when we're working with functions, that means we just need to compose it somehow. And we can do that by building a function. So we know that rest is going to return a function g now. Here it is. And we're going to build a function that, given the x, which comes from the left, so that's the left associated bit, we're going to apply g to the result of f of xy. So we're going to do this left associated bit and pass it on to the future. So hopefully that makes sense. That's a bit of a tricky one to sort of figure out. But it's basically just pulling the trick of function composition. So it's a bit like when you try and make fold R's as fold L's and vice versa. So it's all about using function composition and the identity function. So the next tricky bit is we need to try and get the rest out of the binds to make ourselves a nicer shape. And so what we can do here is we're f mapping some function over rest. So instead, if we make this a parser in its own right, we can put the rest out and app it. So here's what I mean by that. So this time, the result of the two binds produces a pure, and after the entire bind is done, we can app the result onto rest. So it's the same deal, but we've just shifted it around a bit. And hopefully you can see why, because now it's starting to look like the same applicative pattern we had before. We just need to do a little bit more tweaking to get there. So I'm just going to do some basic Haskell algebra things. So I'm going to start by flipping f round so that the arguments are reversed, and then turn this into a function composition. And then what I'm going to do is I'm going to basically take away the G, and I'm going to do that by also flipping the composition. So now we're left with a function that looks like this. That's just some normal Haskell fiddling. And now what we can do is we can try and hoist this flip dot out. So what's going to happen is I can actually just pull it out with an fmap. And then it doesn't matter whether it's in the binds or outside the binds. So similar to the app, we can just hoist it out. And now this is definitely the same pattern that we saw before. So we can just apply that pattern, and we've got something, again, that looks a lot nicer. And again, for completeness sake, what changes in Parsley? We add some codes, and I also use idiom brackets to do the flip dot. So I've made use of those. So that's that. So that's how you can get rid of bind in some quite common circumstances. Obviously, it doesn't work for everything. So if you have an if then else, that's probably a good candidate to start reaching for selectives. So selectives capture the idea of choice and decisions. So it's good to try and figure out how to use those. But what else? So earlier on, I mentioned that we have this problem of no recursive arguments. And I also mentioned that there was a way to get back the full power of bind. I'm going to cover that now. So general principle is registers. So this is something that is unique to Parsley so far. I haven't seen another parser combinator library that's got them. I can be corrected if I'm wrong. I would be glad to know. But so far, I haven't seen anything like this. Parsec has an idea of user state. This is a bit more general than that, I think. So here's the interface. There are 3 functions. There's a question quickly. Can I use applicative do with rebindable syntax to use my app? Probably. I don't see a problem with that. I haven't tried it out myself, but you should be able to. Just make sure that it doesn't try and use bind, I guess. So I haven't tried that out. I have thought about it. I'm sure it probably would work. Right, so registers. What's the interface? So 3 basic operations. New register takes a parser that we're going to store our initial state in, and then takes a function that, given a register, we don't know what those are. Those are completely abstract to us. Will produce a parser B. And the key thing to note is, even though this looks a bit like bind did, where you're saying, well, I've got this value and it's making a parser, actually the registers can be allocated at compile time, so that's not an issue. And essentially it will run this function with a given register to get the value of B out. And how do we actually interact with registers? There's get and there's put. So get, basically, you give it some register that you're interested in, and it will just return that value to you. And put does the same thing, but you give it a parser that will produce the value you want to store. Now, this is a little different from the way that state works in regular programming, where normally we just give it a value. And the reason for that is because we don't have bind, so we have no way of working with the raw values themselves. So as an example, modify, which is normally done something like get bind put.f, we actually write it like this. So it's a bit backwards. So you say put into the register the result of apping P onto get of the register. So first we get the value out, we run the, well, first we run the function, run the parser to get the function out. Then we fetch the value from the register, apply the functions, and then put it back in the register. So we can have as many of these as we want. We can just generate them ad infinitum. They're quite powerful. So let's see what they can do. First thing to note is they're safe. So like ST, they can't leak. So if I try and be cheeky and do pure of a register, that's going to explode. The type checker will hate me for that. And the reason is because it's got this for all R here. So this for all R says that we've got this phantom type variable that doesn't really mean anything. The point is it can't leak. So you try and return it, the compiler will complain at you. Whereas just getting the value at that register is perfectly fine. This is just an identity. This is just equivalent to P. But the point is that, yes, you can get the values out, but you can't return the registers themselves. So selectives couldn't implement join, and they couldn't persist results. Let's focus on the second one of those, persisting results. So here's bind, our old fan favorite, and it takes a parser, it takes the result out at runtime, and it uses that to build more structure, but that should have been at compile time, so it's no good. Selectives can do something similar. It's the sledgehammer approach. What happens is you, for types where you know all of the possible values, i.e. they're enumerable, and there's a finite number of them, and I can look at them at compile time, I can literally try every single possibility in order until I find the hole that fits. It's very inefficient. For small types, it works quite nicely. For bigger ones, it will just completely collapse on its head. What registers gives you is bind. And the signature is a little bit different in that instead of an A, you have a parse array, and that suffices to be enough. So what that says now is at compile time, we have a structure that can generate runtime values, and we can use that to generate more compile time structure. So what's the practical difference and how's it implemented? So if you want to think in terms of monads, it's the same as basically doing a bind where you put pure in front of it. Operationally, they're identical. In terms of how does Parsley do it? Well, it makes a new register that stores the value, and then it calls the function with get of that register. So you can think of it like an immutable view of a register that can be used many, many times. So in parsec, if we have some contrived example like this, we have p bind x, f of x onto q onto return x. In Parsley, we can do that by basically doing the same thing, but instead of using x as a value, it is a parser in its own right. So no return x, you just use x, and we can't say f of x, we have to say f mapped onto x. That's really the only difference. So that can actually get a lot of it back on its own. So the persistence thing is now solved. And we can do a similar thing with argument recursion. And the answer is use a register. So I'll briefly touch on this. Here's a repeat combinator. It should do n lots of p and return all their results in a list. So basically, if n is 0, we return the empty list. Otherwise, we add p onto the front of doing the next iteration down. And all we need to do is store that state that we're iterating over in a register. So the register underscore just means forget about the parser bit. I just want a value put in it. So I start by initializing my register with n, and then I use predicate, which is a selective operation, and basically say if the register contains the value 0, then I'm going to return the empty list, similar to this bit. Otherwise, I'm going to modify my register by subtracting 1. So the state now has n minus 1 in it. And then I'm going to go do p and then onto the front of go. And this go doesn't take any arguments anymore. But the next round of the iteration, that get register is going to return the next state along. And this might look a little bit ugly. Registers can be very nice as long as you've got the right combinators. And in this case, it's the for combinator. And this behaves just like a C-style for loop. So we have an initializer here, parser A. We have a condition, parser A to bool, and a step A to A, and we can make a body and do it lots of times. So repeat underscore, which ignores the results this time, can just be done as initialize with n, while it's not 0, subtract 1, and keep doing p over and over and again. And if you want a slightly different variant that maintains the results, just change it so that it builds up a list of b's as it goes. And so this is the repeat that we just defined. And I think this is a lot nicer as notation. Very briefly, For is really useful for doing context-sensitive grammars. So the traditional A to the N, B to the N, C to the N problem, you can basically think of it as read lots of A's and increment a counter while you're doing it. And then for N, for I equal that counter until it's 0, subtract 1, read B's. And then for C, basically the same for loop, but with reading C's. So you can read N A's and then use that as a counter on 2 loops to read B's and C's. And I think that's quite a nice, concise way of working with context-sensitive parsers without bind. And finally, selectives can't implement join. Registers can. It's a fundamental pain in the ass. Essentially, you basically either go the whole way and you implement an interpreter for the language. So you can implement an interpreter for parsers, and basically store the state in registers and actually implement a machine with it. Otherwise, if you know all of the outcomes statically, use a register to store which outcome you want, and then use selectives to basically choose that outcome later on by getting the register. Either way, registers can do everything. And I know this because I have implemented a Turing complete language in Parsley that first reads the description of the language, then applies it to an input, and it works out fine. So it's quite cool. We've got everything Monads can do, and it's all at compile time. So what's next for me and Parsley? Basically, I want to be able to eliminate registers at compile time. So at the moment, they're implemented with strefs, and with enough static analysis, you can work out, you can find long stretches of them and just eliminate them. If the state doesn't persist across backtracking or something like that, it can be gotten rid of. And the second is actually introduce error messages and use staging to actually compile the way they're overhead. And I noticed there was a question about that in the chat, so I'll get to that. And I think this is a really cool idea as well. So do all your error message generation at compile time, and at runtime, you don't have to carry it around. And that's that. So now I will go to questions. Thank you. And at the same time, I will take a look at the Slack. So yes, error messages should not really affect performance. It's okay to pay once you know you have an error, yeah. And that would indeed fit quite well with the stage approach and having lots of information. So yeah, exactly. That's what I want to work on. So a lot of the job of building error messages, I think you can do at compile time. The bit you don't know is the exact position or what character caused the error. So at runtime, that's the sort of thing you want to start to synthesize. But you don't want to carry around this information and be building up partial error messages at runtime. I think that's just a complete waste of time in a very literal sense. So yep, I've answered all of those. Yeah, so in the text parser combinators library, they did start using it applicatively. I was very happy to see that. I was also very intrigued to see the ternary operator, which uses a clever use of join. That is one of those instances where it's really, really, really quite painful to get Parsley to implement it, unless you develop an entire Parsley meta interpreter, which I have been tempted to do. Wouldn't recommend trying it yourself. Wonder if someone's worked on a complete procedure, then applicative do, which knows. I don't know if this exists. It would be amazing if there was something that could transform applicative monadic operations into applicative ones a bit more, because that would, I think that would basically eliminate everything I've just talked about, which I'd be very happy to see. So yeah, at the moment, I think it can handle basic applicative structures, and it will give up every now and then and generate a bind, even perhaps when it's probably not necessary. So I don't know to what extent it can go, whether it's totally complete. I imagine probably not, especially as you have to find the optimal solution. But again, that's what Parsley's for. So yeah, is there anything else? I see a question being typed. Yeah, so it can't handle then and previous. And those are quite important. From a Parsley standpoint, they're quite important because they can be implemented incredibly efficiently. So usually you use like const, you fmap const over something or fmap flip const to start building those combinators. Parsley actually special cases them And the reason it does so is because in a stack level, they can be implemented with pop as the pop instruction that pops from the stack. So they're really quite nice, and they can be very, very, very well optimized by the Parsley engine if you use them. Yeah, so is there anything else that we haven't covered or talked about so far? I think I've allowed you to all unmute yourselves, so that's fine by me. So if I can expand this as well. Stop sharing, there we go. Okay, it seems then.
Sorry, can you say something about performance? Like, have you tried to benchmark it? As
in Parsley?
Yeah.
Yes, that was in the ICFP paper. The results were pretty conclusive. It's bloody fast. Basically, in comparison to stuff like megaparsec and attoparsec and parsec, it can be over 3 times faster than them. It has been known to beat Happy as well. And it came within, I think it was within 30% of the performance of Bison, which is the C parser generator library. So we always expected Bison to be faster. We need a bit more work before we can get that out of the way, but it is a very, very fast library. Its only drawbacks are when Template Haskell stands in your way, essentially. But as Template Haskell improves, Parsley will also improve.
So I understand you tried, in the ICFP paper, you tried it on the JavaScript grammar.
Yeah, it's a slightly older version of the JavaScript grammar, I think. We plan soon to unite with some other people and generate a common bunch of grammars and benchmarks that we can use to compare lots of different things in lots of different circumstances. So it'd be good to see, instances where parser generators are just intrinsically better and so on. So we're going to work on that.
Mm-hmm.
But yeah, the JavaScript parser that we were using was a slight subset of JavaScript. I think it didn't handle stuff like classes, but it was mostly complete. And we did run it on some pretty big programs like a big number library, which surprisingly is a lot of lines of code. It was bigger than I thought it would be.
Cool, thank you.
A question?
Yep.
Yeah. Can you hear me okay?
Yeah, I can hear you okay.
Sounds okay. Okay, cool. Yeah, thanks. So I noticed your branch operation. I'm afraid I haven't read your paper yet, but I'll read it soon. The branch operation looks an awful lot like the coproduct operation. You have an A to a C and a B to a C, and you get an A plus B to a C. But it's like not quite that. If you reshuffle the parameters, it's still not quite that.
Yeah. So
if you had a category that had the F of A arrow B, that's your category. Yeah. You think it could be that? Could your branch be? It takes an F of A to C and an F of B to C, and it gives you an F of A plus B to C,
of A plus B to C, an F of A plus B to C. Ooh.
Yeah. So right now if you reshuffle the arguments, you get an F of A to C and an F of B to C, and then you give an F of A plus B and you get an F of C. But could you combine that? The last F of A plus B.
I think conceptually maybe. From a practical parsing point, the answer is no. The reason for that is you have to think about the order of execution. So the idea is that first you execute the condition so that you know which branch to take. If you have the branches up front and you want to generate a function, that's okay. What you'll end up doing is executing both branches to get both their payloads. So if you only want to execute one, then you need to make sure the condition's done first.
Where does that ordering come in? Is that something about the semantics of your parsers or something?
It'll be the semantics. So there's a difference in the selective functor worlds between strong and weak selective functors. So the strong one is the one I've got where only one of the branches is executed. at most one. In weak selective functors, which you can implement with applicatives, you will run both branches. So that might be you're doing static analysis, you want to know both their effects. And in order to make the function, which is what you want at the other end, where you produce the function as part of the payload, you need the weak one. So you need to say, I need to run both branches. And then once I have both results and I've run them both, then I can make the function that when given the either that comes in can arbitrate. Because you do need to.
And are you concerned just about efficiency, or are you concerned about semantics too, like some kind of effect?
So semantically, it would be different because you would have to execute both branches. You have to do one after the other.
Yeah, it's just the word execute I'm trying to like went on. Is there necessarily a notion of execute? Is there necessarily
yeah. So
where does that come in? Is that something about because selective functors get to do that if they want to?
So because selective functions are all about effects, here we're focusing on the parsing effect. So let's figure out what would happen if we changed from a strong selective function to a weak one. So we might have something where we wait on either to come in. We don't know how that works. And on one branch, we read an A, and on the other branch, we read a B. So if we work with a weak selective functor, we're going to either, one way or the other, depending on which way your semantics would work, we're either going to read an A, then a B, or a B, then an A. But the point is that actually we only wanted to read one of those two things. So we've executed two effects that shouldn't have been executed together.
And does this notion of effect, so if you think about parsing, you don't necessarily need it to have effects, right? Because parsing is a very simple semantics, it has nothing to do with effects. Where do effects come in your story? Does it come in wanting some kind of generality of selective functors, or is it something really motivated by parsing?
So actually, yeah. So this is sort of where my supervisor wants to take me with this, Nick Wu.
Yeah. And
the basic principle is that parsing is an effect. It's the effect of reading a token. That's all there is to it. And then you compose it with state and non-determinism, and you get parser combinators. So very basic level, state T of maybe is a possible what do you call them? It's a possible model for the semantics of Parsley is a state T maybe. And so you can treat that as the free state plus non-det is.
Yeah, but state isn't, I mean, I don't need to go on about it. It just seems that state parsing has nothing to do with each other, right? Parsing is something like mapping a string to a Boolean or mapping a string to some more information, and then there's no notion of effects.
The state
seems like maybe you're bringing in effects unnecessarily.
The state effect is there to carry the input. That's what it's there for.
Yeah, but that's like an optimization, right? You don't. That just makes parsing more efficient.
I'm not sure about that.
Well, maybe we can correspond about it.
Yeah, maybe. I think maybe, yeah, you could do something where you just pass the input all down all different branches and you don't consume out of them. But there is definitely an effect associated with it. In some way, shape, or form, there are effects associated with parsing. If you choose to think of them down the effect handler route.
Yeah, which I wouldn't, because it doesn't have a simple mathematical semantic. That's fine.
Maybe if Nick is, who knows, maybe Nick is milling about in the shadows. If he's not, then yeah, I might not be qualified at the moment.
Yeah, sure. Okay. I'll send you both a note.
Okay.
All right, thank you.
Thanks. Okay. That sounds like it might be it. Yeah. Thanks a lot for listening.
Thank you very much. And maybe I can request a big applause for you. Yeah, it was very impressive seeing how you can remove all the bindings and replacing by simple code.
Yeah, it's an art form. I like to think of it as an art form, one that's well worth learning, in my opinion.